Okay, good afternoon, Senior 5. I want to begin by doing correction of this work that I had given you about radioactivity. The first question was asking you to define radioactivity, and the answer is here. I had given you a neighbor question, and its answer is here. Radioactivity is the spontaneous disintegration of a radioactive unstable nuclei with emission of radiations, and radiations we said the radiations are alpha particles, beta particles, and gamma rays. So a question can be state explain what is meant by radioactivity. There you can go ahead and give the radiations that are emitted. But if the question says define, then you can stop here because after all, there was another question asking you to give the types of radiations. Name 3 types of radiations emitted during radioactivity and state how they affect the nucleus of a radioisotope. The particles are beta particles, alpha particles, and gamma rays. Then how do they affect the nucleus of the radioisotope sample? Most of you just stated and you forgot to give the effect of those particles. So after stating, you score the marks there, then you now say beta particles. Beta particles, we know they have no effect on the atomic mass, but they increase the atomic number. One of you answered by saying they increase the atomic number and stopped there. Now I was asking, does it increase the atomic number by 5, by 4, by what? So you have to be specific in chemistry and say beta particles have no effect on atomic mass, but increase the atomic number by one unit. So you must mention that to score that mark. Again, that person said alpha particles increase the atomic mass and decrease the atomic number. That's not right. You have to be specific. Go ahead and say alpha particles decrease atomic mass by 4 and atomic number by 2 units. And give examples there. Give an example of an equation where in this equation you see a beta particle is emitted, and if it is emitted, the atomic number of this element, which is bismuth, has decreased. The atomic mass of this element has increased by 1. That's why it is 84 here. So when a beta particle is emitted, the atomic mass is not affected, but the atomic number increases by 1 unit. So also give the example of when an alpha particle is emitted. The gamma ray has no effect on the radioactive sample. The gamma ray has no effect on the radioactive sample. So the mass number, they are on the atomic number and mass number, but reduces the energy content of the nucleus when it is emitted. So the gamma ray has no effect on both the atomic number and mass number, but reduces the energy content of the nucleus, because when it is emitted in form of energy, so the energy content of the nucleus reduces. Let's go to the other question. In this question, we had asked you to plot a graph. Now, I noted something about the way you are plotting the graph. When you are plotting a graph, your graph should have a title. Your graph should have a title. There is a mark for it. A graph of mass of that element against time. Your graph should have title. I'm saying title. It should have scale. The scale should be appropriate. Then it should have axes with labeled units. Axes should have units. So these are marks. The title is either 1 mark or half a mark, but the scale and axes, they take the 2 marks. That one is a must. So if you did not label the axes, you know that you lost 1 mark. And you get that mark when you label the axes with units. If your work does not have units, then still you will lose the mark. But now I want to assume that you are all good at plotting the graph. I want to take you through the question that was asked. After plotting our graph like this, the question was determine the half-life. Determine the half-life. How do we determine the half-life? I told you the other time, and we agreed that you can begin with a mass of 60, which is the maximum here, and the half of 60 is 30. So 60 is on the axis for time is at 0. So at 0 seconds, the mass is 60. So you start counting from 0 to get the half-life. Then the one for 30 is this one. See that dotted line until it meets the graph. So I calculate that time from 0 up to where this line is, this one that has come from the graph, and that will be my first half-life. That will be my first half-life. To get the other one, I can use any other mass. For example, now I note this one as my first one, and according to me, I'm getting 64 from my graph, but I can use another mass. For example, I can use 30. From this 30, the half of 30 is 15. From this 30, its a half is 15. So I draw a dotted line on until it meets the curve, and I again bring it down. So I again measure the time from this line of 30 up to the line of 15, and I get the time within, and that will be my second half-life. So when I get my second half-life like that, it means the half-life of this sample will be the average of the 2 half-lives, this one for 60 and 30, and this second one for 30 and 15, because a half of 30 is 15. So half-life T a half will be this T1 plus this T2 out of 2, and I get my answer, which will be in seconds. Now after getting half-life, the other question is always determine the rate constant. Now to determine the radioactive constant, lambda, you don't have to use this expression of 2.03, because in that one, to get the constant, you don't have the time taken. Because in this expression, there is where you are going to find time somewhere. So if you don't have time and you don't know you know the initial mass, it is 60, but you don't have time, so you cannot use this expression. But instead, since you already have the half-life, you are going to say that from this expression of t a half equal to natural log of 2 out of lambda, then you will be able to get the lambda, this constant, because natural log of 2 is constant and the half-life, you have gotten it from this expression. So this is how you are supposed to get lambda. And lambda, since you are dividing by t a half, which is in seconds, its units, it should be in per second, since you are dividing by t a half, which is in seconds. Then when you get lambda, you can be able to answer any other question. Then you can be able to use this expression 0.3 log n out of n naught equal to negative lambda t to answer the questions that follow, because they may be asking you about the time or the mass. There you can use that expression and you'll get the answer. So that is the correction for that part. That is the correction for that part. Please go through it and get the answer for half-life and the radioactive constant. I want us to now look at something else. I wanted to give you an assignment about drawing shapes of molecules, which I think you had studied, but I felt I should first remind you what we go through together. Before we start drawing the shapes of these molecules, there is something that we need to always remember, and that is the valence shell electron repulsion theorem and molecular shapes. How does it state? It states that the electron pairs around central atom in a molecule do repel each other to attain stable arrangement in space, where there will be minimum repulsion between them and maximum angle of separation. So they repel each other such that there is maximum angle of separation and minimum repulsion between them. Now, what else is important? How do they repel each other? You remember that according to this repulsion theorem, the lone pair to lone pair repulsion is greater than lone pair to bond pair, and this repulsion is also greater than bond pair to bond pair. I'll keep on explaining this as we go on. The repulsion between two lone pairs is greater than the repulsion between a lone pair of electrons and a bond pair. And this repulsion between a lone pair of electrons and bond pair is also greater than the repulsion between bond pair and bond pair. I want us to, having known this, we can start now looking at the shapes of molecules. We start looking at the shapes. Now, in the first case, here, we have a molecule where we have one electron which is shared. We have molecules where there is one electron and that electron is shared. An example is hydrogen molecule. Hydrogen molecule contains two hydrogen atoms. Now, remember we have always been saying that a covalent bond is formed by sharing of two electrons, where each hydrogen donates an electron. So this hydrogen has donated one electron, and this hydrogen has also donated one electron to form this bond. That's why we are saying these molecules, they have one electron, and that one electron is shared. So each of them has one electron, and that electron is shared between the two atoms. So this electron from this hydrogen is shared, and this electron from this hydrogen is also shared. So which shapes do those molecules adopt? Those molecules adopt a linear shape. And an example is here. We are saying it is hydrogen, and we also have another example, which is hydrogen chloride, whereby hydrogen donates one electron and chlorine also donates one electron towards the formation of that bond. Now, part B, we have two electron pairs where they are all shared. We have two electron pairs, but those electrons are all shared. And a good example is here, where we have beryllium chloride. Now, another thing that you need to know is when you are drawing these shapes, to know the number of electrons that are participating in bonding. They are always the outermost electrons. There is another way of writing electronic configuration which we use in A level, but if you have not yet studied it, you can use your O level knowledge. For example, beryllium has its atomic number is 4, meaning its configuration is 2 to 2, if you remember. So the valence electrons for beryllium are 2 electrons. So beryllium uses 2 electrons for bonding. But chlorine, it has 1 electron in the outermost energy level, so it uses 1 electron for bonding. So to draw the shell of beryllium chloride, it means beryllium has 2, it becomes the central atom. So 1 electron is shared to form this bond, and the other electron is shared to form this bond. Then each chlorine atom also donates 1 bond, and that's how the shape of beryllium chloride is formed. Another example is carbon dioxide. Carbon, it has 4 electrons in the outermost shell, meaning those 4 electrons should participate in bonding. But oxygen has 6 electrons in the outermost shell. But what is its valence? Its valence is 2, meaning each oxygen atom should be having 2 bonds. Each oxygen atom should be having 2 bonds. So carbon, it has 4 electrons. So the 4 electrons, each electron participates in formation of a bond. Then oxygen, it has the valence of 2. So each the 2 electrons one forms this bond and the other one forms this bond, then the other one forms this bond and the other one forms this bond, like that. Now if you look at this, for carbon disulfide it is the same story, because sulfur has 6 electrons in the outermost shell, meaning its valence is 2. When we look at this shape for nitrogen, remember carbon has a valence of 4, so and nitrogen has a valence of 3. So that means the 3 electrons of nitrogen participate in formation of these 3 bonds. Then the other bond for carbon, the other electron for carbon participates in formation of this bond, but hydrogen has a valence of 1, so that is the structure, like that. So when an atom is a central atom like carbon, you use its outermost electrons, and when it is not a central atom, a central atom, I mean the one which is in the middle and it is surrounded. When it is not a central atom like oxygen, you can use its valence electrons, which are 2. Let's go to part C. In part C, we have 3 electron pairs, and those electron pairs are all shared. We have 3 electron pairs, and all those electron pairs are shared. So this is what I've been telling you. For example, boron. Boron, its configuration is 2 to 3, because its atomic number is 5. So meaning it has 3 valence electrons. So all the 3, what we are saying, 3 electron pairs, it means all the 3 electrons are shared. In other words, they are participating in bonding. So in that case, those molecules, they take the shape which is called trigonal planar. We shall be asking you to draw the molecule, then you name the shape that is formed by that molecule. So where a molecule has 3 electrons, and all those electrons are shared, where it has 3 valence electrons and all those electrons are shared, it should take this shape, which is trigonal planar. 3 electron pairs and all of them are shared. They take the shape of trigonal planar. An example is boron trichloride. Boron trichloride. Boron trichloride, it means each bond of boron and chlorine is formed by a pair of electrons. That's what we call electron pair. A pair of electrons where boron donates 1 and chlorine donates 1, and all of them are shared. So that is a trigonal planar shape. Then we have this one where boron is the central atom and the other atoms are methyl groups. The other atoms are methyl groups. So these methyl groups, CH3, they are already bonding with the 3 electrons of carbon. That means 1 electron of carbon which remains is the one bonding with chlorine. So that's how this one is coming by. But what do you have to note here? Since there are 3 electrons and they are all shared, the repulsion is going to be equally distributed. Because here there is no lone pair of electrons which has more repulsion than bond pair. If these are all bond pairs, then the repulsion is equally distributed, and when you rotate you form an angle of 360. So since there are 3 atoms, each of them between a bond and a bond, the angle formed is going to be 120, such that 120 times 3, you get 360. If you look at sulfur trioxide, remember I told you when it is a central atom, you use its valence electrons or the electrons in the outermost shell. For example, sulfur, it is 2 to 8 to 6, so it uses 6 electrons. So when you look at this, you realize that there are 2 bonds between sulfur and oxygen. So on each pair of bonds here, sulfur will be using 2 electrons. And oxygen, since it is not a central atom, it will be using its valence, which is 2 electrons. So one electron to form this double bond between sulfur and oxygen. If oxygen has a valence of 2, then it should always form double what? Double bonds with sulfur. Take note of that. Take note of that. And now here, this is a double bond here between nitrogen and oxygen. This should be a double bond. Nitrogen and oxygen should be a double bond. Then nitrogen and oxygen should be a double bond. Then where there is a negative charge, you put a single bond, because this negative charge represents addition of a pair of electrons, where one comes from nitrogen and the other one comes from oxygen. So this positive charge there, it means that nitrogen lost a pair of electrons, and that pair of electrons came to oxygen. In other words, it was like this. Then this bond was broken. Then this bond was broken, and when it is broken, nitrogen that has broken the bond gets a positive charge, and oxygen gets a negative charge. But most of the time we don't show the positive charge, and we just draw our structure like this. Just draw our structure like that for the nitrate. So take note of that. So the positive charge in the middle there should not confuse you. It means it was like this, then the pair of electrons was lost. And when a pair of electrons is lost, the one that has lost gets a positive charge, and the one that has received gets a negative charge. So let's leave that at that. But what do we have to note? That when we have 3 electron pairs, and they are all the electron pairs, and they are all shared, there is no lone pair of electrons. The shape is trigonal. The shape is trigonal planar. And another good example is a carbonate ion. As you can see, I've already told you that when you put negative charge, it means the bond was broken already between carbon and oxygen. So there was a bond between carbon and oxygen, and it was broken, meaning carbon lost the electrons and oxygen gained them. That's why it has a negative charge like that. So that is the structure of a carbonate. But the angles should be equal for trigonal planar, and the angles are 120. So let's look at another structure, other structures. Now other structures here is where we have 3 electron pairs including a lone pair. 3 electron pairs or 3 pairs of electrons, and on those 3 pairs of electrons there is a lone pair. What do we mean? On those 3 electron pairs there is a lone pair. An example is here, as you can see, sulfur dioxide. Now sulfur dioxide, it has 2 oxygen atoms, but the central atom is sulfur. We agreed that the central atom uses the electrons in the outermost shell, which are 6. So we should see 6 electrons of sulfur. Now, the other surrounding atoms, which are oxygen, for them they use valencies, and the valence of oxygen is 2. So meaning oxygen donates 2 electrons, and sulfur also donates towards the formation of the bond, meaning we should have uh, 2 bonds, because oxygen donates 2 electrons, one for formation of this bond and the other one for formation of the bond up. Even sulfur donates. And since there are 2 oxygen atoms, we have that oxygen donating 2 and sulfur donating 2 to formation of this bond. But sulfur is the central atom. We have agreed that should use the valence electrons, which are 6. So it means if it has donated 4 so far to the formation of these 4 covalent bonds, it means one pair is remaining, 2 electrons are remaining, and that's what we call a lone pair of electrons. And we always put it in a circle like that, a lone pair of electrons. But from the start we said the repulsion between a lone pair of electrons and a bond pair, this is a bond pair, This one here is a bond pair, where there is a bond and on the bond there is a pair of electrons. That is a bond pair. So the electrons on sulfur and oxygen, that is a bond pair, but this one is a lone pair. So the repulsion between a lone pair and a bond pair is greater than the repulsion between a bond pair and a bond pair. So this lone pair is going to repel this bond pair of electrons, and they will end up coming like this. They will end up going this side, such that the angle between the lone pair this is my lone pair and the bond pair, the angle between the lone pair and the bond pair is greater than the angle between the bond pair and the bond pair. So this angle is between the bond pair and the bond pair, but this angle is between the lone pair and the bond pair, and it should be bigger than this one, which is between the bond pair and the bond pair. So those molecules, they take a shape called V shape. So V shape or bent shape. So the shape formed by such a molecule is called the V shape. But the angle between the lone pair and the bond pair, this angle should be seen to be greater than the angle between the bond pair and the bond pair. And that is why you see the structure looking like this. 4 electron pairs and they are all shared. 4 electron pairs and they are all shared. The 4 electron pairs are distributed tetrahedrally, and the central atom is, and these are distributed tetrahedrally around the central atom, and this accounts This accounts for the tetrahedral shape. This accounts for the tetrahedral shape. So here there is no lone pair of electrons. They are all bond pairs. They are all bond pairs, and they repel each other in this way. So if you have 4 electron pairs, this is an electron pair, 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 and they are all shared, we are saying the shape they form is a tetrahedral shape. That one I will not take a lot of time on it, because you can see that is the shape they take. Meaning, if I take an example of like a sulfate is the central atom, so its 6 electrons should all be 6 electrons in the outermost shell should be used in bonding. This is my sulfur, and it has 2 negative charges. Now, what does that mean? Where there is a negative charge, I put 1 bond, because it means that they were 2 like this, then 1 broke. One broke, so oxygen that took that pair of electrons should have a negative charge. That's what it means. So when there is a negative charge, I put 1 bond, like that. So that is the structure of the sulfate ion, and it is called a tetrahedral shape. It is called a tetrahedral shape. Four electron pairs including a lone pair. 4 electron pairs including a lone pair, meaning only 3 electrons of the central atom are participating in bonding, and the other one is a lone pair. An example is ammonia. Nitrogen. Since it is the central atom, it means it has to use all the 5 electrons which are in the outermost energy level. 1 electron from nitrogen is used there to form hydrogen. Another electron is used there. Another electron is used there. Now 2 electrons are remaining, and that is what we call a lone pair of what? Electrons. 2 electrons are remaining and they are not bonding. We call them a lone pair of electrons. Now it should be seen that the angle between this lone pair of electrons and this bond pair here with hydrogen is greater than this angle here and this angle there. So this angle should be greater between lone pair and bond pair. Take note of that. Let's look at another structure. Let's go to this one. For the notes you will go through, I believe you even already have notes that Mr. Kafuma gave you. I'm just helping you to remember. 4 electron pairs and including 2 lone pairs of electrons. Now, in this case, oxygen is a central atom, like I've been telling you. So if oxygen is a central atom, it should use all its 6 valence electrons, which are in the outermost shell. So, a good example is water. When you have water, it has 2 hydrogens. So oxygen has used 1 electron to form this bond between oxygen and hydrogen, and it has used the other electron to form a bond between hydrogen and oxygen. So it means if oxygen has used 2, then 4 electrons are remaining, and those 4 electrons are not participating in bonding. So those 4 electrons, we call them 2 lone pairs of electrons. 2 plus 2 is 4. So water molecule will have 2 lone pairs of electrons to make the total 6, because one has formed this bond, another one has participated in formation of this bond, meaning 4 remain and they are not bonding. So I have to draw my lone pairs of electrons like that, as you can see. But remember, the repulsion between a lone pair and a lone pair is greater than the repulsion between a lone pair and a bond pair. So I expect my lone pairs to repel themselves greater than the one for a bond pair. So the angle between these two lone pairs should be greater, because the repulsion between lone pair and lone pair is greater than the repulsion between lone pair and bond pair. Then again, the angle between the lone pair and the bond pair should be greater than the angle between the lone pair and the lone pair. So you find your outer molecule finally having this shape. So, and this angle should also be greater, this one should be greater than this. So this becomes the valid structure. The angle between two lone pairs should be greater than the angle between a lone pair and a bond pair, and that should also be greater than the angle between a bond pair and a bond pair. So that's how the two lone pairs of electrons come about. If the atom is a central atom, it should use the number of electrons in the outermost shell. Then if it is not a central atom, it is surrounding atom, it should use its valence. Another example is here. Chlorine. I have this chlorine O2 with a negative. Chlorine now is going to be a central atom surrounded by 2 oxygen atoms. So it has 7 electrons in the outermost shell. So we write chlorine, oxygen being no, in this case oxygen is a central atom. Oxygen is the central atom, sorry. Oxygen is the central atom, and it is surrounded by 1 chlorine, which has a valence of 1, and 1 oxygen. No, there are 2 oxygens. Yeah, I think this structure has a problem. Let us do this one, where oxygen is surrounded by 2 chlorine atoms. Now oxygen has used the 2 electrons already, 1 here and another one here. That means 4 are remaining and they become lone pairs of electrons. And that shape is also called the V shape. The shape formed there is also the V shape. So water molecule also forms the V shape. What about phosphorus phosphorus pentachloride? The shape is just called the trigonal pyramidal shape, and it is like this, where phosphorus is the central atom, chlorine, and chlorine down. That is the shape for phosphorus pentachloride. So you go through your notes with that explanation, then I will ask you to draw for me shapes of some molecules.